by using the graphical representation. Let us see that firstly equation for position time relation, right? Now we have represented the graph as shown that the initial velocity of a car is u and the final velocity is v and the time taken is mentioned as t. Now let us assume or let us suppose to draw a parallel line that is named as AD, which is parallel to OC. Now in order to find out the velocity of this particular car is noted as the area of this trapezium, right? This whole area will be giving the acceleration of a car, that is velocity by time, right? Therefore we can say it consists of one triangle and one rectangle. Therefore the area of the triangle plus area of the rectangle will give us the whole acceleration of the car. Therefore it will be area of rectangle is half AD into BD, that is base into height, plus the area of a rectangle, that is length into breadth, that is OA into OC. Now we can say that AD as T, right, and BD as, that is V minus U, because the total is V and the length OA or DT is equals to U, therefore it is given as V minus U. Therefore we will be saying half into T into V minus U plus OA into OC, that is OA is U and OC is T, therefore UT. And we simplify this, we will be getting half UT minus UT plus VT plus UT, that is 2, that is VT by 2, right? Therefore we can say that we will be representing the S as half T into AT plus UT, that is UT plus half AT square. We have previously known that BD equals to AT, we have simplified, that is change in acceleration. Therefore we are getting the position time relation as S equals to UT plus half AT square, right? And velocity time relation we have derived that previously, that is V minus U equals to AT. And let us derive the equation for position velocity relation, that is S equals to area of the trapezium, right? We have find out, and S can be written as OA plus BC, that is OA plus BC into, that is the two sides, that is the length covered, into OC, that is the breadth, that is length into breadth, by 2, because it is the average speed it is taken, therefore it is divided by 2. Then we will be seeing that OA plus BC equals to U plus V, and OC is the time taken to travel the distance. Therefore we will be representing that U plus V into T by 2, but we have learned that T is equals to, that is from first relation, that is velocity time relation. Here T is equals to V minus U by A. Therefore we will be representing T, that is we are substituting the second equation in first equation, and we will be getting U plus V into V minus U by 2A, and therefore we will be getting S equals to, that is 2AS. The denominator is sent to the left side, therefore 2AS equals to V square minus U square. This is the third relation, that is between the position and velocity. By this we have derived these three relations, and let us see one problem in order to understand briefly the relations between the position, time and velocity. Let us assume that a train is starting from a rest position and it is attaining a velocity of 72 km per hour in 5 minutes, and assume that acceleration is uniform, and we have to find out the acceleration and the distance traveled to attain that velocity. This is the problem in order to understand the three relations, that is velocity time and position time and velocity position relations, what we have studied previously. let us solve the problem and let us find out first the acceleration. We have known that velocity and time relation, that is v minus u equals to at. V is the final velocity and u is the initial velocity, a is the acceleration and the t is the time taken to travel the distance. Now let us see that v is 72 kilometers per hour, right? Therefore 1 kilometer equals to 1000 meters and 1 hour equals to 60 minutes and 1 minute equals to 60 seconds. Therefore 72 into 1000 by 60 into 60. It will be resulting into the units. We are converting the units from kilometers per hour into meters per second. Now we will be getting 72 into 5 by 18 and 18 fours are 72 and we will be getting 20 meters per second. Okay. Now we can remember the formula, that is 1 kilometer per hour is the conversion equals to 5 by 18 meter per second, or else 1 meter per second equals to 18 by 5 kilometers per hour. This is the conversion of units from kilometers per hour to meter per second and meter per second to kilometers per hour. You can shortcut, I can say the shortcut how to remember the conversion also. In order to convert from smaller to higher units, that is meter to kilometers, we use the bigger number, that is 80 in numerator and 5 in denominator. From higher to lower, we will be using the lowest number, that is 5 on the numerator. And thus we can remember the conversions also. And u is the initial velocity, it is 0 meter per second. Therefore, we will be applying the 20 minus 0 by time taken is 5 minutes, that is 5 into 60. We will be giving the seconds. Therefore, 20 by 300, that is equals to 1 by 15 meter per second square. This is the acceleration of the train in units meter per second square. Now let us see the distance travelled by the train to attain this velocity. Now according to the velocity and position relation, we will be getting that s equals to v square minus u square, right? That is s is equal to v square minus u square, or s is equals to 2as equal to v square minus u square. By substituting those values, we will be getting s as v square minus u square by 2a. Therefore, v square equals to 20 meter per second. 20 minus 0 by 2a, that is 2 into 1 by 15. And we will be getting 20 into 20 by 2 into 15. Sorry, that 2 into 1 into 15. This 15 will be going upwards and 2 1 tens are 200 into 15, that is 3,000 meters. It is equal to 3 kilometers, right? Therefore, the distance travelled by the train is 3 kilometers to attain an acceleration of 1 by 15 meter per second square. In this manner, we can find out the relations between the velocity, acceleration and time by using these three equations. Let us see the uniform circular motion of objects. Now let us see that, for example, an object will be changing its velocity when it is having the difference in magnitude and direction, right? If at all an object doesn't change its magnitude and if it changes only the direction or the path in which it moves, then the objects will be as shown in the figure. That is, let us take one, suppose the car is moving or a person is moving with the same magnitude and he is changing his direction as shown in this figure ABCD. In this figure, he is changing his position or he is changing his direction 4 times. That is, from forward direction to downward and downward to leftward and leftward to upward. That is 4 times he is changing his direction, but the magnitude is remaining constant. That is AB and BC, CD and AD are remaining the same, right? There, and you can see this is as rectangular track of the person. And at the same time, when he moves in an hexagonal track, that means he is changing his direction at the time of hexagonal. That means 6 directions is changing, or 8 directions it is octagonal track. And in the same way, when he is changing his direction alone, then the track will be as shown in different figures, but the magnitude will be same. When we take that a circular track, that is, his magnitude is same, but he is changing his direction with respect to the center point, right? Therefore, this type of motion is known as accelerating motion, where there is change in velocity with respect to direction only. Therefore, we can say that I can give a best example for acceleration motion, that is the fan, which is rotating in a circular motion, right? The wings of the fan will be rotating, and also the washing machine, which is rotating in round circular direction. And also when a person carrying a stone with the help of a thread, when he rotate it will be rotated in the circular motion, right? These are the good examples for the circular motion of the objects or the acceleration motion in circular way. Here the magnitude will be same, but the direction will be changed. Now let us see that when an object moves in a circular path with uniform speed, its motion is called uniform circular motion. That means the magnitude doesn't change. It is constant throughout the motion, but the direction itself changes in a circular manner. Then that motion is known as uniform circular motion, right? For example, a person carrying a stone with the help of thread, and when he rotates it, it will be representing a uniform circular motion, right? Now let us define the change in velocity or velocity of a circular motion. Velocity of a circular motion is defined as the rate of change in distance by time, that is the total time taken or the total distance covered by the object by the total time taken to cover that distance, right? Now we have seen here the circumference of a triangle is 2 pi r, we know that. Therefore the radius is pi r square, right? The area of a triangle is pi r square and radius r, the circumference will be 2 pi r. Therefore velocity equals to the total distance covered, that is total circumference of circle, that is 2 pi r, by the total time taken, that is t. Here we are representing the uniform circular motion velocity v equals to 2 pi r by t. By this we can conclude the motion of different objects, that is uniform and non-uniform motions and circular motions, and the motion or the flow of an object in a straight line path, and the relation between the position, velocity and time, and the definitions such as acceleration, distance, speed, displacement, velocity and rate of velocity. All these terms we have learned in this chapter, that is motion.